So we're going to start looking at series, and that's what's going to happen when you start summing up the terms in a sequence. So this is an interesting sequence, 1 over I squared, I equals 1 to infinity, so it's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc., all the way on out. Now, the big thing we're going to look for is whether or not a series converges. Now, if a series converges, really what that means is that the series adds up to a finite number. That is, this adds up to a finite number. Series converges if it adds up to a finite number. Doesn't matter what that number is, just as long as it's less than infinity. So that's nice. And interestingly enough, this series does converge. In fact, we have calculated exactly what this is. There's a guy by the name of Leonard Euler who figured that out first. It's amazing that it converges to something. It's even more amazing that somebody calculated it. It turns out to be pi squared over 6, which is like, wow, that's a cool series. Somehow, the sum of the reciprocals of the squares is related to the ratio of the circumference of a circle to its diameter. And you square that and divide by 6. Wow, pretty cool. All right, we're not going to work with something this challenging. That was something that was pretty difficult to solve, but Euler was quite the genius. We're going to work instead with geometric series. We touched on this in section 11.1. Let me remind you of a geometric series. It would look like this: the sum from n equals 1 to infinity of a sub 1 times r to the n minus 1. Now, you don't have to put an a sub 1 here. I just do because of habit. But if you started by putting in an n equal 1, I get n minus, or 1 minus 1 is 0. R to the 0 power is just 1. So the first term would be a sub 1, and then a sub 1 times r plus a sub 1 times r squared, and so on, all the way out to infinity. And the thing about a geometric series is that you have this common ratio, r. So that's their common ratio. And that's what you're multiplying by to get from one term to the next. Now, another way you can think of that is if you take this term and divide it by the previous term, you're always going to get that same ratio, r. And there's something special about geometric series that makes them really cool to work with. And that is, if the absolute value of r is less than 1, then the sum of this series, n equals 1 to infinity, a sub 1 r to the n minus 1, can actually be calculated. And that sum is a sub 1 over 1 minus r. Well, this has to be a strict inequality. Can't be equal to 1. Has to be less than 1 in absolute values. You could have negative values for r. It's just as long as their absolute value is less than 1, that's when they're going to converge. So let's take a look at some examples. So we'll call this one example A. And we're going to have 5 minus 7 plus 49 over 5 minus 343 over 25, and so on. So the first thing to try and figure out is this a geometric series? Well, it's not terribly clear. But what you can do is calculate r for various combinations. So I can look at the ratio of these two right here and get R is -7/5. So that's for those two. And let's look at these two. Are we going to get the same value of R? So R would be 49/5 divided by 7. And that does give me, it should be -7. And that does work out to -7/5. So I'm getting the same thing again. And you can start to see that, oh yeah, if I multiply by -7/5, -7/5, -7/5 from one term to the next, I keep on getting the successive terms. For instance, -7 times 49 is -343, 5 times 5, 25. So it works. So what does that tell me about the series? Well, if R is greater than 1, or absolute value of R is greater than 1, then the series diverges. So diverges means it doesn't converge. So it means it sums up to infinity in some loose sense. So, okay, I mean, it's not too much of a shocker here. -7/5 and absolute value equals 7/5 greater than 1. So the series diverges. Maybe I should section this off for geometric series in a geometric series. So this is a general statement, and this is what's happening with our particular series. So, okay, not so bad there. Let's try another one, unless there's some questions or comments on this one. So, for example, B. Now I'm trying to give you a good variety of examples here, so that way you're in good shape when you go to your WebAssign homework. So the sum from n equals 1 to infinity of 25 times 0.59 to the n minus 1. And looking at these things, sometimes it might be tough to see whether or not it's actually a series or a geometric series. So it's not a bad idea to write out the first few terms. So let's do that. So n equals 1, n equals 2, n equals 3, n equals 4, and so on. So let's see. N equals 1, that'd be 25 times 0.59 to the 0, and then 25 times 0.59 to the 1, 25 times 0.59 to the second, and so on. But to get from one term to the next, what are you multiplying by? What's our common ratio?
Less than 1.
Yeah, 0.59. So that does a couple things for us. First of all, the series converges because absolute value of R is less than 1. So that's nice. But there's a bonus here for this problem as well, and that is we can actually figure out what this series converges to. And that series would converge to, well, I need a couple things here. So S equals A sub 1 over 1 minus R. A sub 1 is the first term. What's the first term of our series? Well, 0.59 to the 0 power is really 1. So the first term of the series is actually 25 over 1 minus 0.59. And we could do this in our heads, that's fine, but yeah, what's the point? Let's use a little technology on this one. We'll take 25 divided by, that'd be 0.41. And then I'll hit the math key, press answer to fraction, and I get a nice little fraction out of this. So 2,500 divided by 41. All right. How's that one looking? Questions on example B here? All right. Well, let's keep rolling. Does anyone ever notice how towns and cities and countries compete heavily for big ticket events like the Olympics or the Super Bowl? So here's a little example from economics for you. Suppose that the Super Bowl is coming to town. Now, Super Bowl 40 came to Detroit, and the NFL estimated that they were going to spend $50 million in the city of Detroit, which is pretty cool. That's a lot of money. But the thing is, that money doesn't stay in somebody's pocket. It gets respent. So you take that $50 million, bars and restaurants have to buy food, pay employees, pay taxes, pay gas. So let's say maybe 80% of that gets respent. And that money gets respent again. So 50 million times 0.8 squared. And then that money gets respent, and so on and so on and so on. And if you look at this, this is actually a geometric series. It's a geometric series with a sub 1 equals 50 million and r equals 0.8. So, all right, let's figure out what the sum of this series is. So we'll call this example, let's see, so what our third example? Yeah, example C. So the third example is, or excuse me, the sum is going to be 50 million divided by 1 minus 0.8, and that's going to turn into 250 million. And that's starting to sound like a lot of money. Now, this economic multiplier effect, you know, is true to an extent. It's not a perfect model of what goes on, but you can see that, you know, an initial injection of cash really does have, you know, a pretty big impact, assuming that this is, you know, somewhat true. And it seems like a reasonable assumption, but I'm not an economist. I'm not going to debate that part of it. Just wanted to show you kind of a good homegrown example. All right. Let's see. Let's do a couple more. This one's kind of curious. What if x is 0.499999999 repeating? Is that going to be less than or equal to 5? What symbol would you put here? Less than or equal to?
Equal.
Equal.
All right. Well, let's find out. We can actually do this as a geometric series. So what this is it's, you can think of 4.999, et cetera, as 4 plus 0.9 plus 0.09 plus 0.009, etc. Now we don't have to work with the 4 part here. We can just work with this part of the series. So let's look at 0.9 plus 0.09, etc., and try and figure out what to do about it. One thing that you need to notice is that this is a geometric series. Can anyone tell me what R is for our geometric series?
0.9/4.
No, we're not going to worry about the 4. 4 is not really going to be part of that geometric series. We're just going to work with the 0.9 part.
So it'll just be 0.999. 0.999, yeah.
Well, let's see. The idea for finding R is to take the ratio of 2 adjacent terms. So I could look at 0.09 divided by 0.9,
Which is 0.1.
or 0.009 divided by 0.09. Yeah, and I think I heard somebody say it. What'd you get for R?
0.1.
0.1. 1/10, right? By moving the decimal to the left 1 place, you're really multiplying by 1/10, 1/10. So cool. Now, if I want to figure out the sum here, then let's see. I need S is going to be a sub 1 over 1 minus R. Looking at this part here, what's a sub 1?
Would it be 0.9?
Excellent. It would be 0.9. And so what I get is 0.9 over 0.9. Can someone pull out their graphing calculator and figure this out for me? So this whole thing turned into a 1. Okay. So,
Hey, right.
Hey, that's right. All right. Looking good there? Okay, let's add to our mix here a little bit. An infinite number of mathematicians walk into a bar. So, an infinite, isn't that cool? That's a lovely thought. Infinite number of mathematicians. Now, the first one orders 1 beer. And the second one orders half of beer. And the third one orders 1/4 of a beer. Can you figure out what the next one orders?
1/8.
1/8 of a beer. And before the fifth one can order, the bartender says, stop, stop. And he puts 2 beers in front of him. He says, you know your limits. All right, I know you're at home all muted. Otherwise I'd hear huge guffaws of laughter. Well, let's see if he's right. All right, so this is a geometric series. You should give me some love on that one. Come on, there's not too many people that tell these math jokes.
I just got it, by the way.
I laughed.
I enjoyed it, yeah.
All right, that's good. Thank you, thank you.
Took me a minute.
This is a geometric series. A sub 1 equals 1. What is R in this for us?
It's half.
Yeah. I always, I know it's called the common ratio, but I think, well, what do I multiply to get from one term to the next? It seems to be easier sometimes. So the sum is going to be 1 over 1 minus 1/2, 1 over 1/2, whoa, 2. Pretty cool. All right. By the way, one thing that this says about the number 5 is that there's 2 ways to write it, 2 equivalent decimal ways to write it. as 4.999 repeating or the number 5. And that's just a little hint for one of your WebAssign questions. There's 2 possible decimal representations of that number. Let's see, where example F, I guess. So we'll do kind of another one like that. This time we have a number like 3.478 bar. What does that bar mean?
Repeating.
It's repeating.
Yeah, the 478 part is repeating. Okay, so that little part here that's repeating is the part that we can use as a geometric series. And to see that, let me write it as 0.478 plus 0.000, and then my repeating part, 478 plus 0.000, 478, and so on. Now, if it's not clear to you already, this is a geometric series. To figure out what R is, you could take this number and divide it by this number. So why don't you do that on your calculators and see what you get. See if someone can't beat me to the punch. Oh, you lose. So R is 0.001. 0.001. And for the repeating part, we can replace that repeating part with a sum. This is a geometric series. If you wanted to write it in a fancy way, you could. You could write it as the sum from n equals 1 to infinity of 0.478 times 0.001 to the n minus 1. That would be what this looks like in terms of series notation. Call that sum S. But because it's a geometric series, we can calculate it this way. I'll take my first term, 0.478, divided by 1 minus 0.001. And that turns into 478 over 999. So we're almost done. I want a nice fraction for this thing right here. So this number can be written as 3 plus 478 over 999. And let's just turn that part into a nice mixed number, an improper fraction, I should say. This is a mixed number. Remember how to do that. You take this times this and add it to that. So 3 times 999 plus 478.
I think you're missing the decimal. Missing the decimal for 478.
No, actually I'm not. I appreciate that. What happens is that the decimal can cancel out. So you're right, the initial answer is 0.478 over 0.49 or 999, like that. So you are correct there. But if I multiply everything by 1,000 over 1,000, that's technically multiplying by 1, right?
Yeah.
But instead of canceling, I'm just going to shift everything. So I appreciate you checking me on that one. But we can get away with this. I just didn't show my steps, so my bad on that. Thank you. To finish this up, I did my multiplication, and I ended up with 3,475 divided by 999. Let's check it. Let's see if that actually works out the way we expected it to. So I'll take this number, 3475 divided by 999. Perfect. 3.478 repeating. Just what I was expecting. Okay. Let's take a look at a slightly different example. 0 to infinity of x minus 4 to the n divided by 7 to the n. So the question is, for what values of x is the series convergent? That's a good question. Well, let's take a look at a few terms in this series and try and get a handle on what this means. So I'll write out maybe 3 or 4 terms, n equals 0, n equals 1, n equals 2. I think I'll get bored there, so we'll just do 3 terms. At n equals 0, let's just cut to the chase. Anything to the 0 power is 1. At n equal 1, I got x minus 4 over 7. And then at n equal 2, it's x minus 4 squared over 7 squared, and so on. What's the important observation you have to make in order to move forward? What can you tell me about this series?
There's a variable in it.
There's a variable in it, yeah. And that's going to mean a little bit more work for us. What kind of a series is this? Can you tell me what the next term is without looking up here? Can you see the pattern?
Would it be cubed?
Yeah. So you're multiplying by
By
x
power
minus 4 over 7. So basically, this is a geometric series. What is R?
X minus 4 over 7.
Perfect. Thank you. X minus 4 over 7. So in order for a geometric series to converge, what do we know has to be true about R?
Less than 1.
Has to be less than 1. So absolute value of R is less than 1. Let's see what that means. So that would be absolute value of x minus 4 over 7 is less than 1. Now, since 7 is already positive, if I multiply both sides by 7, I end up with this equation. Absolute value of x minus 4 is less than 7. And hopefully it's not been too long since you solved these kinds of problems. This would mean negative 7 is less than x minus 4 is less than 7. In other words, the absolute value of this has to be trapped between positive and negative 7. Okay. Now if I add 4 to both sides, I end up with negative 3 is less than x is less than 11. So this series will converge for values of x between negative 3 and 11. Now I'm not sure what kind of notation they're going to ask. They might ask for it in interval notation. That would be this. How come I'm not using brackets here and I'm using parentheses instead?
It's not equal to them.
Yeah, it's not a less than or equal to, it's just a less than for both of these. So neither one of these contains the endpoint. At the endpoint, things may be different. In fact, they would be different. They wouldn't converge. Cool.
I'm kind of confused. did you get the 7 on the right side from? Like when you have the absolute value of x minus 4 is less than or equal to 7?
I multiply both
left.
sides of this inequality by 7. So I multiply by 7 on the left, and I multiply by 7 on the right. That way I'm doing the same thing to both sides. Now the 7 on the left canceled with that.
I see.
7 on the right just gave me the 7.
You were trying to get rid of that fraction. So.
Yes, yeah.
Okay.
And I can do that because technically what's going on here, because that's just a 7, I can think of that as, let me see if I can write it in a different color here. I can think of that as the absolute value of x minus 4 over 7. That is, I can take this out of the absolute value since it's positive anyways. So that's how I can get rid of that 7. All right.
Okay. Yeah, I get it.
Cool. All right. Let's take a break here. So I want to come back and we'll start up when I get back with the nth term test.